Don't worry about it.
So it's time for the next talk. Today we have a Chris here. He'll tell about the Twitter's quest for a Holy Graal runtime. Let's start.
Sure. Ooh, that's loud. That's a very loud microphone. Welcome. I think you all have seen the keynote today, and you're waiting for Kenny Bastani. No, he's not coming. So he asked me, he couldn't come, so he asked me to do a presentation. So that's it. We're going to talk about Twitter. And we get to the most embarrassing question. Who in here has a Twitter account? Yeah, well, I know the ex-Soviet Union countries, they like to use Facebook. You don't guys like to use Twitter that much. But we'll change that today. Well, maybe not. So I'm asking you to tweet about this whole conference, the whole event, all the sessions you're going to see, the ones you like. Tweet about it or Facebook about it. I don't even know what that's called. And if you're going to tweet about my talk, add that hashtag TwitterVMteam, because believe it or not, Twitter has a small VM team, and it's not that small anymore. We have about 8 people, and 3 of these people are GC engineers, so they are constantly busy dealing with all the GC problems we are having, like everyone on the planet has. Then I'm a compiler engineer. I do the fun stuff. I do compiler stuff. We have other people doing some infrastructure work, and someone's working on a tool called Autotune, which I'm going to talk about in an hour. So if you want to see me again in an hour, I give another talk. So add that hashtag if you tweet about my talk. And if you don't have a Twitter account, create one right now. I'll check on my phone if you created one. So what's the goal of this talk? The goal of this talk is to save money. That's the goal. So when I started, well, let me talk what I did before I started to work at Twitter. I'm working on JVMs for a very long time, like over 14 years, and all these 14 years I worked on JIT compilers. So I'm going to ask you a few questions so we're all on the same page. People know what a JVM is, right? JVM? Yes? JVM? Good. Hotspot? Yes, the JVM of OpenJDK. Who knows what a JIT compiler is? Oh, quite a few people. So for the ones who don't, in a nutshell, it's basically when you compile Java or Scala or any language down to Java bytecode to a class file, the JVM takes that class file and runs it and interprets it, and then at some point it compiles it on the fly while you're running your application to native code, just in time. That's a just-in-time compiler. You know, compared to an AOT compiler, which means ahead of time compiler, like GCC or something, right, where you get an executable. A JIT compiler does it while you run. So I'm working on JIT compilers. I used to work at Sun and Oracle in the Hotspot compiler team, so I worked on Hotspot on JIT compilers called C1 and C2, mostly C2. Do people know what C1 and C2 are? Yeah, cool. Some experts here. So C1 and C2 are 2 JIT compilers in Hotspot. C1 is sometimes called client compiler, and C2 server compiler. You might have heard client and server before. You remember the dash client, dash server we used to use years and years back. So C1 is a high throughput compiler. So the purpose of C1 is to get away from interpreting code as quickly as we can to run on native code, but it doesn't do a lot of optimizations. And then C2 is a highly optimizing compiler, which uses all the fancy optimization techniques that we have, you know, a lot of inlining and escape analysis, loop unrolling, auto-vectorization, you know, all that stuff. So these are the 2 compilers. These 3 projects are the biggest ones I worked on at my time at Sun and Oracle. JSR 292, Invoke Dynamic. You might notice one for dynamic language support in the JVM. We worked on this, John Rosa and I, for quite a while, and there were about 2 different implementations. The first one was a lot of handwritten assembly code, which was a pain to maintain and also a pain to write, and we had to port it to all the architecture that we supported. And then we found out that we actually have a performance issue. So we redesigned the whole thing and moved all of that logic, that handwritten assembly logic, into Java. into a package called java-lang invoke. And that's obviously Java code, and I wrote a lot of that Java code. So if it doesn't work, you could technically blame me, but I always say the code I wrote was perfectly fine, and other people who touched it after me, they broke it. So CHEP 243 is a Java-level JVM compiler interface, also called JVM CI. We introduced that in JDK 9, and it's basically, let me ask that question. People know what Graal is, right? Graal, yeah? Not Graal VM, I'm talking about Graal. So Graal VM is an unfortunate marketing term, as I always put it. It's like an umbrella name for 3 different technologies. One is Graal, the JIT compiler, right? Who knows what a JIT compiler is? All hands should be going up, I explained it. So Graal is a JIT compiler, and then there's something called Truffle, which is a framework to implement language runtimes. And then there's something called Substrate VM, which you might know as native image. It's that piece of code where you compile something into native code. So I'm talking about Graal, the JIT compiler. When I say Graal, I mean the JIT compiler. So we took the interface, by the way, Graal is written in Java, if you didn't know that. So we took the interface that Graal was using to talk to the JVM, to a hotspot, and extracted it and made it a module in JDK 9. And it's not an official API, but it's kind of stable-ish. So since 9, 10, 11, 12, is 13 out, I don't even know. There's an interface, and you can plug in an external JIT compiler on the side, like Graal. And then we did CHEP 243 mostly because of CHEP 295, which is ahead of time compilation. This is not native image, this is something different. This is basically a small command line utility where you pass in class files or jar files, and then it sends off all the methods that it finds to Graal. Graal compiles it, and it spits out a shared library at the other end. We implemented this, we introduced this for improving startup performance. So if you have a very big application that takes a very long time to start up and executes a lot of different code, this might help. The main difference between this one and native image is technically not Java. Well, this is actually Java. All right. And now I work for the greatest company on the planet. And it's not Facebook. No, it's not. Okay. So what is Twitter? Right? You might know. But it's a huge distributed system comprised of many services, right? We have hundreds of microservices. The biggest ones we have is the tweet service, user service, timeline service, social graph service. These are all the services that you need to build something like Twitter, right? And we have many JVMs per service, thousands of machines running thousands of JVMs, and we have multiple data centers. So there is some scale to it, right? And so we're getting back to that scale part when we talk about the money part. I already talked about, open source, sure. Let's talk about Twitter and open source. We do a lot of open source. We are also using a lot of open source. So there is this GitHub, I always forget what it's called, like there's a Twitter GitHub thingy where all of our open source projects are. So if you're interested in that, go to that link, check it out. So for us, Graal is a very good fit because it's also open source, right? We just take it and put it into our JDK. We build our own JDK, by the way, and we just stick it in. And we're actually contributing to, I'll give you a small example later what we contributed back, but my colleague, Flavio, he's actually, and I'm talking a little bit more about this in my second talk, he's writing some Scala-specific compiler optimizations in Graal. So we're doing some stuff there. We have our own JDK, as I just mentioned. It's based on 8 update, right? Who is running 11 in production? Ooh, a bunch of people. Didn't expect that. So it's a little different than OpenJDK 8U because we backported CHEP 243 because we needed it for Graal, right? We have a Graal copy in it, which is basically what you get on GitHub. We just cloned it into our own repository. We have something called Contrail, which is a JFR replacement. That's basically moot now because Oracle open sourced their JFR implementation. So when we move to 11, we don't need that anymore. We have a few things in Contrail that are better implemented than in JFR, especially asynchronous logging. So we might contribute that back at some point in time. And we still have a few CMS improvements, but they're also, as we all know, CMS is deprecated, so who cares? All right. So why Graal? Why do we want to use Graal? C2, has anyone in here seen C2 code? Okay, I didn't expect that, but it's a very old and very complex compiler. It truly is. When I started working at Sun Microsystems, and I've worked on JIT compilers before, the learning curve is way too steep. It took me about 3 to 4 years to fully understand what the hell is going on. This is a ridiculous amount of time, right? No one of you, I would think, would sit down and learn a compiler for 4 years, right? It's ridiculous. I get paid for it, so I mean, why not? So the last few years, we didn't do any major optimizations in C2. So we didn't implement a better escape analysis. We didn't improve inlining, not really. I'm lying a little bit because we did a small tweak for JSR 292 for method handles. But for regular code, there's no change. The only thing that we are doing, and when I say we, I mean the OpenJDK community or Oracle, basically. The only thing we're doing in the last 4 or 5 years is basically when Intel's coming out with a new chip architecture with wider registers, Intel is writing new intrinsics. Intrinsics are basically replacements for method in the core library, and they are mostly handwritten assembly code where you use AVX 512 and all these things for, let's say, string.indexOf, right? Because you can write it more efficiently in assembly than a compiler could ever do. These are the only things that we are doing. There's no, C2 is basically in maintenance mode, which is very interesting because the whole world runs on Java, but we are not really improving C2. In my opinion, C2 has reached the end of life a long time ago. So that's why we, and I especially, I'm trying to get away from C2 to something that's a little easier to understand, and that's Graal. So Graal was, from the beginning, designed with a modular sense, not module in the JDK 9 sense, because we also run on 8, but you can see, like, this is a very old screenshot of Eclipse of all the projects they have. It's basically like a JDK 9 module. It's a project that's one unit of code. There's architecture-independent code, and then there's architecture-dependent code, and the build system makes sure that architecture-dependent code or architecture-independent code doesn't depend on architecture-dependent, all these things that you don't want to do. And circular dependencies, all that doesn't exist, which is very much true in C2. So, and then on top of it, which is like at the very bottom, but it's the most important point, Graal has especially better inlining and escape analysis. So do people know what inlining is? All right. So inlining is basically when you have a piece of code in your source code that, it's the same code multiple times, you refactor it into a small method, right? And you call it from everywhere, which is very good practice. But in terms of runtime, it's not very good because we have to call that method. So what the compiler does, it takes that piece of code that you just extracted and puts it back into your code. Because then we can optimize more. The more code we have, the bigger our worldview is, the more optimizations we can apply. So that's inlining. And escape analysis is, it can get rid of object allocations if the compiler can prove that we don't need it. I'm not going too much into detail here, but that's kind of it. It can get rid of object allocations, which reduces, GC pressure and so on. And so C2 has a very, I don't want to say basic, but the very first, there were 2 papers basically. The first paper, that's what C2 implements. It's the basic escape analysis implementation. And then Graal has something that's called partial escape analysis. It's an enhancement of the first one, and it can get rid of more object allocations than C2 can. So this will be very important later on, and especially in my second talk. So bugs. This talk, as I said, it's about saving money, but it's mostly, I'm telling you the story of me working at Twitter for the first year, roughly. I joined, we ported all the stuff, and then we started running Twitter services on Graal, and we found some bugs, which was good, right? So I'm going to talk you through the bugs a little bit. So bug number 1, and they're all still on GitHub, so you can read it up and if you want. Graal should support same OSR compilations as C1 and C2. So OSR means on-stack replacement. It's a very technical thing. I'm not going too much into detail what it is, and it doesn't really matter, really. But so I was running the tweet service, I think, and I was looking at print compilation log output, and I saw these guys saying OSR with logs not supported. And the exception we got was this one, which is very nice, right? Because it's written in Java. Actually, when something goes wrong, you get an exception. That's really cool. And then you see there's an on-stack replacement phase, and it tries to do something, and it says, OK, sorry, I can't do that. So we discussed this. So there's an engineer at Oracle Labs called Tom Rodriguez. So we discussed this situation for a little bit, and we decided that it's not a big issue because tiered compilation will take care of it anyway. Do people know what tiered compilation is? Yeah, 1.5. So you remember when I talked about C1 and C2, that there are 2 compilers in Hotspot. Other JVMs also have something tiered compilation like OpenJ9, they do something similar. You start running your application and you interpret it, right, which is really slow. And then, as I said, you compile with C1, but you compile it in a way that it compiles in code that collects profiling information. So it collects data like how often was that method called, how often did we execute that loop, what types did we see, and then later on, after a while, we take that profiling information and recompile with C2, right? So that we get peak performance code, and we step through the tiers. That's tiered compilation, right? So if the top tier, in Hotspot there are about 4 tiers. 1, 2, 3 are all C1 tiers with different levels of profiling support or gathering. And then tier 4 is C2 or Graal, the top tier compiler, right? So if we can't compile that method with the top tier compiler, we still have compile code from C1. So it's not that bad. And this particular method was not a very hot method, right? It compiled later, much later. It was not really in the hot path of our tweet service. But still, it would be nice to fix it, right? So after a while, David, he fixed it. And as you can see, it's about 1,000 lines of code to fix that bug. And technically, it's still open. No, wait, the other way around. It was fixed by this guy. And then I was running, I took in the fix, and I was running the same tweet service to figure out if it fixed the issue. But then these other 2 popped up. There were other problems here. And as you can see here, Tom says there's a little piece of logic in C2's parser which allows access to static fields within CL_init, the static class initializer, for classes which aren't fully initialized yet. Wrap your head around it. So basically, we are trying to access static fields in the static class initializer, but the class isn't initialized yet. It's kind of, a chicken and egg situation. This is, so we found a new bug, right? Byte comparser should allow access to static for uninitialized types. This is the little bit of logic in C2's parser. The method, as you can see, is called static field OK in CL_init, which already tells you what we're trying to do. We can do that because we are the compiler. We are compiling the method that's initializing the class, so we know when we run that we can trust the value of the field. Yeah, right? We can do that. So there's this comment, and the second line of the comment says, better to check now than to de-optimize as soon as we execute. So do people know what de-optimization is? Probably not. So de-optimization, you know. You want to explain it? No? OK. So de-optimization happens, C2 and Graal are speculative compilers. So they assume something while we compile to produce better code. If later it turns out that that assumption isn't true anymore, we have to de-optimize. So basically, we have to kick out the compile code because it's not valid anymore, and we fall back to the interpreter, right? And then we run on the interpreter again, we go through the whole tiering that I explained to you and recompile the code with the new information we have. That's the optimization. The problem with the CL init is, how many times get the static class initializer executed? Once, right? So if we compile the static class initializer, that means either two things. Number one, it's very long, very big and very long, or it has loops in it, right? And we want the static class initializer to finish as soon as possible because it potentially holds up all of our application, right? I mean, there might be threads that are doing other things, but most of your system probably waits for that one class to being initialized to carry on. So if we're already running it interpreted and it takes a very long time to the point that we actually get to compile it, and then we compile it, and then immediately when we run the natively compiled code, we realize, oh shit, that doesn't work, and we de-optimize back into interpreter, we lost a lot of time, right? It would have been better we kept interpreting. So that's why this is very important. We fixed it, 31 lines of code. As you saw, it's like a tiny little piece of code, the method. And I think the 31 lines actually included a test case, if I remember correctly. So that was a small fix, but important. Then we had this one, a fatal error. That's not good. It's a crash, like a seg-v type of thing. The problem with this one, as you can see in my comment, is with long-running processes, couple days. That was very annoying. So I was running the tweet service, and after a few days, it fucking crashed. And I had no idea why. And so I was looking around, and I really didn't know what to look for, right? And so it turns out I was searching around in our configuration file. What are we passing to the JVM? Is there anything we do? And it turns out we're using an agent called Heapster. And Heapster is available on GitHub. It's an agent library to do heap profiling for JVM processes. So heap profiling usually works with bytecode instrumentation. The problem here is that Graal is written in Java. So if you instrument bytecode, you're also kind of instrumenting Graal. So we were discussing this, and it turns out the double dot value off, there's like an intrinsic, as I explained earlier, it's called method substitution. It just replaces the code with something else. And that method substitution in Graal is using double dot value off, and that method uses new. And new is something, since we are doing a heap profiling, it gets instrumented. So that's an issue. And then, these two, they're discussing it, and then Doug at the end says, okay, maybe it's time to bite the bullet and parse the bytecode for snippets. Snippets is another thing like intrinsics, and their callies directly, right? So the problem is we are parsing them as regular Java code, but we can't because we can't allow it to be instrumented. So they did this, and they fixed it with 2,800 lines of code. That was a big change, right? But it was very important. So Oracle Labs, they were running Graal, forever and years and do their testing and run spec GBB so many times. But this is real world. Like everyone's using fucking agents and do bytecode instrumentation. So this was a very important thing to fix, and I'm glad we found it. Then we had this bug where some netty tests failed. So I was running, I think, again, the tweet service, and for the longest time, sometimes in the logs, I saw these connection exceptions flying by, and I had no clue where they were coming from. The problem is, microservices are nice, but if something goes wrong, it's hell, right? Because you don't know where it's coming from. If my service gets a connection exception, is it me, or is it the other 100 I'm talking to? And for me, the microservice architecture was something completely new. So I had no clue what to do and where to start looking. So I let it sit for a while, and then at some point, I think we updated the Netty version. So I decided to run the Netty test suite. So I ran it, and as you can see, Netty buffer, boom. So that one failed. So okay, that's interesting. So we looked into this one, and this is a very interesting bug. So there is something called reverse bytes, it's on the number class, so you can do integer.reverse bytes, right? It reverses bytes. In this particular case, it was short.reverse bytes, and as you can see, it did it wrong, right? Which is ridiculous because it's used all the time. But in this particular case, it produced the wrong result. So then Tom found out, blah, 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 blah. It does eliminate the reverse completely. So basically what the bug was, it was a copy and paste error. Don't ask me why it worked in the millions of other cases, but just in this particular one it didn't. But it was a bug. And only 68 new lines of code, and that certainly included a test case. So it was basically one line of code. We fixed one line of code. But it was, again, very important to do this, to run it on real-world code to find all these issues. So contribution, I only have one in here that I did a while ago. I wrote this slide deck before JDK 9 came out. So I was looking into, so JDK 9, if you may know, has something called are they now called compact strings or compact strings? We had both of them. I can't remember which one is now what they called it in 9. But, compact strings, there it is, chap 254, compact strings. So JDK 9 has compact strings, and the way Oracle decided to implement this, and I was very upset about it, was with handwritten assembly code, like the intrinsics I was talking about earlier. I wanted the implementation to be unsafe-based, so that all the compilers could benefit from it, but unfortunately C2 wasn't smart enough to optimize it well, and so they went with the handwritten one. That means all the handwritten intrinsics that they did, we have to port over into Graal. It's ridiculous, but we have to do it. And as I said earlier, the important conversations that compact strings does, like making it wider and compressing it down to 1 byte, it's using all these SSE, AVX, AVX 512 instructions so that it's faster, and we need these in Graal as well. So I implemented one of them, the biggest one. This is a benchmark. The top is Graal without the intrinsic, and the third line is kind of the important one with the longest string size. It's 2,600 something, and then with the intrinsics, it's 126. So that's not faster than C2, but it's the same performance, right? We need feature parity with C2 if we want to replace C2. We need all the stuff that C2 has in Graal as well. So I did this. I didn't finish the work, I have to say, but Dimitri, he actually fixed it. And as you can see, it was about 1,000 lines of assembly code, assembly instructions that I had to port over. But it's basically copy-paste. You just have to from C++ to Java. But it was still, it's stupid work. We don't really want to do it. Okay, so that was kind of the introduction. Now we're going into numbers. So I'm going to show you a bunch of graphs and tell you about our tweet service. So the tweet service is a Finagle thrift service. Finagle is one of these open source frameworks we have. You can get it on GitHub if you're interested. It's an extensible RPC system for the JVM used to construct high concurrency servers. I have no idea what it is, but I don't have to. I work on the JVM. I don't care what's happening above me. So the important thing with this one, it's 92% Scala code, right? Good. So this is my test setup, and I have, if you're doing compiler, especially compiler, but in general, if you're doing performance comparisons, and maybe the single-digit percentage improvement, you always need dedicated machines, because otherwise everything you do is in the noise. If I do this in the data center, it's certainly in the noise and we wouldn't even see an improvement. So I have dedicated machines per instance configuration. All instances receive the exact same request. That's very important, not the same number of requests, but the exact same request. That's important for the tweet service, because a tweet could be 1 character long or 280. Right? And the memory allocation pattern for the two is very different. But we want to compare apples to apples. So we run this JVM CI version, this Graal version, not that important. Default tiered C1 Graal setup, I explained to you earlier. We run tiered compilation with C1 and Graal. We still compile with C1 and then later recompile with Graal. Yeah, Graal bootstrapping, I'm not going too much into this one, it's basically since Graal is written in Java, and we are not doing AOT compilation for Graal yet, but there's a project out there that will do that. It has to compile itself, right? When you start up your JVM, it has to compile itself. That's called bootstrapping. And it takes a little bit, but I have a talk where I explain that it's actually, do I have a slide for this? No, don't. All right. So I have another talk called Graal, how to use the new JVM jig compiler in real life. You can find it on YouTube, where I explain all the bootstrapping and memory allocation, I don't want to say issues, but the situation as it is today, if you're interested. And you should be, by the way. So this is the tweet service. This is requests per second for 24 hours. We are comparing C2 in blue and orange is Graal. Ignore the JDK 9 bits. Again, as I said earlier, I wrote the slide deck when we all thought JDK 9 would be the next Java version. Right, JDK 9 that Java no one ever used. The important thing about this graph is that all received the same number of requests, right? That's all we want to see here. So, excuse me. So this is PS scavenge cycle. So the tweet service uses parallel GC, and we are looking at GC cycles here. So this is C2 over 24 hours. It's kind of it fluctuates with the load. And then if we do Graal, it looks like this. So we certainly reduce the number of GCs when we run on Graal instead of C2. And it's, 9, right? I forgot that we're talking about 9 here as well. It's about 2.5% less GC cycles. It's not a lot. But remember, we are still doing the same amount of work. Right, we're still delivering the same number of tweets to everyone, but we're having 2.5% less GC cycles, which is great, because GC cycles always affect your latency. Good. Then, this is something I should mention, because for some people it's important, and some of our SREs, the people who take care of our services, some paid close attention to their metrics, and I'm glad they did, and they screamed, oh my God, memory leak, which in fact was not. Graal is written in Java. So it runs in your JVM, and it's just as any other Java application you're running. That means it uses old gen, because it has some state, right? It also uses metaspace, because it has to load classes, right? It's just the way it is. But it's not a lot. It's about 40 megabytes of old gen that it uses. And it's not a fraction of your old gen, it's just 40 megs, right? That's the state. If your old gen is 100 megabytes, it's 40. If it's 2 gigabyte, it's 40, right? It's the same, doesn't matter. But it's good to know. User CPU time. That's the one I care the most about. Because if we can reduce user CPU time, that means we can serve the same amount of tweets with less machines. And that means, ultimately, we will save a lot of money. That gets us back to the money-saving part. So user CPU time, that's C2. That's Graal. It's obviously less, as you can see, than I think 9 now, yes. I really have to take the 9 slides out. Oh, yeah, right. Let me go back one. My other slide deck is slightly different. One thing you might have noticed is there's no y-axis. And the reason why there is no y-axis is because I'm not allowed to show you actual numbers of these things. So the way I did it to visualize is that I made it a ratio, which is actually kind of neat, because then you can see it's flat across the 24 hours, right? It doesn't matter if the load is low or high. It's the same improvement. And that improvement is 11%. And that's a lot. If you can reduce user CPU time and still serve the same amount of requests per second, 11% is huge. That means for the tweet service, and the tweet service has thousands of instances, right? We can use 11% less machines to do that. That means a lot of money. That means less electricity. That means less cooling, all that stuff. So basically what I'm trying to do is I try to save the world here. So please help me out. So user CPU time. The tweet service runs 100% on Graal in production for 2 years now. right? So everything you're seeing on Twitter, or everything you tweeted in the last 2 years, was done by code compiled by Graal. And you should tweet that right now to make sure it actually works right. There are a bunch of other services that run on Graal, the user service, the social graph service, you know, they're like 20 or 30 at this point in time. One thing that I was interested in, I didn't explain too much escape analysis, but I think you have a rough idea what it is. I wanted to know if the 11% improvement that we're seeing, if it's just escape analysis or something else as well. So I did an experiment where I turned off escape analysis for both compilers. And this is the run. I compare C2 and Graal. That's just a request per second, like a different day, the curve looks different. And this is the outcome. So that's PS scavenge cycles with no escape analysis. They should be the same because we're not getting rid of any object allocations. They are, so that's good. And now let's look at the user CPU time we're saving. And that looks like this, and you can already see it's less, and it's about 5%, which is very interesting to me because it's basically half of the 11. So we get about half of the improvements, or the half of the improvements we're seeing with Graal are coming from inlining or other optimizations, and the other half is coming from escape analysis, which is very powerful. So this was very interesting to me. So how much money do we save? Well, I can't tell you. I can't even show you a y-axis, so why do you think I can tell you how much money we're saving? So, but let's make up some fictitious company, right? Maybe you have a data center or some cloud instances you're paying for, so you have a rough idea of how much you're paying. These are some cloud providers I found publicly on the internet that actually give you prices. And they might be a little too high, but you know, again, it's just a back of the envelope calculation, so take this with a grain of salt. This is basically the outcome. So it's between $72 per CPU per year you're paying and $210. So if you're taking away one thing from this presentation, pick your cloud provider wisely, right? Because if you pick the wrong one, it doesn't matter what chip compiler you're using, you're losing so much money. It's ridiculous. So let's say the average, right? Let's say $127 per year per CPU core. So how many cores are we talking? There was an article from Bloomberg in 2014, which is already 5 years ago now, ridiculous, 2 million servers. So it says something here, where does it say that? Estimate puts Amazon over 1.5 million servers globally, and then another analyst says 2 million. Then we have Rackspace, 100,000 servers, Microsoft, 17 regions. Microsoft CEO Steve Ballmer said over 1 million servers with its data centers, blah, blah, blah. A lot, right? So this is a lot of money. Twitter is not as big as Amazon, Google, and Microsoft, and your company probably as well. But let's pick a random number. Let's say we have 1,000 servers. Might be a little too big for your company, but for Twitter, it's certainly not. And each CPU has usually 24 cores today, right? So that means $127 per CPU core times 24 times 1,000 is $3 million. You would have to pay $3 million to run whatever you are running annually. If you can save 11% of this, it's $330,000 that you are saving per year. That's more than I get paid, right? I mean, I don't know how much you guys get paid, but it's certainly more than I get paid. So can we get more improvement? And this is basically my second talk, which is right, I think at 12:10 or something. I'm going to talk about this then, where I'm going to talk about this machine learning framework that we're using to optimize even more than what you just saw. But one thing I wanted to know before I did these machine learning experiments was, can we actually tune the compiler so that we can get even more improvement? And so I sat down an afternoon, about 3 hours, and was twiddling around with some command line flags. And then I ran an experiment. I actually used this, you might recognize this graph, this curve, because it was the same day that the first experiment, and then we have this new purple color, that's my experiment. So PS scavenge cycle, you've seen that graph before, and then this is my experiment, which you can see, yes, it's better. and it's about 1.5% better, which is very good because we only had up to a total of 4.2, right? So I basically improved about 50% more than just what Graal did. And I thought that's pretty cool. I was very proud of this. This is user CPU time. We can certainly see an improvement. And then again, in the ratio, it looks like this. And it's another 2%. So on top of the 11 that we had initially, another 2%. And I was proud of my 2%, right? Because 2%, remember, $300,000. So 2% is about $60,000. That's nice for an afternoon. Yeah, I was cool and proud of this. So any official support for all of this? Because I'm assuming that you don't have a VM team. Probably not. So JDK9 contains Graal, as I said earlier, because of CHEP 295, because of ahead of time compilation. Since JDK9, there is Graal in it. You can just turn it on with that, right? That's all you have to do. And even better, since JDK 10, Oracle decided to make CHEP 317 experimental Java-based JIT compiler. So it's now an experimental feature. You still don't get the full Oracle support if you want it, but if you run it and you crash, they will probably look into it and fix it, right? Because it's in their interest. So it's certainly out there. Since 10, 11, and you got some people run on 11, so for you, it would be very easy to switch over. Oh yeah, that's the thing that I was mentioning earlier. So if you want to know about, you want to learn more about how to use it and run it, watch this talk on YouTube. It's very entertaining, much better than this one. No, I'm kidding. And then there's something called Project Metropolis, which is kind of getting traction now. John Rose proposed this in September 2017, so it's been a while ago. And let me zoom in on the, oh, I thought I had to zoom in on this guy. No. So down there, what does it say? Incubate advanced Java and Java implementation techniques for hotspot, which basically means replace existing features in the JVM with a thing that's written in Java instead of C++, like Graal, right? We replace C2 that's written in C++, something that's written in Java. And it actually says at the bottom, our starting point is earlier proposals for using the Graal compiler and AOT static compilation technology to replace Hotspot server compiler and possibly other components of Hotspot. So that's the goal of Metropolis, to write more of the JVM in Java where it makes sense. Right? For the compiler, it makes sense because it's easier to do. It would make sense to implement the bytecode verifier in Java. It would make sense to implement the interpreter in Java. It would not make sense to implement the GC in Java. And we know all this from projects like Chikes RVM, if you know that, or Maxine. So Chikes RVM was IBM and Maxine was Sun Labs. It was basically a meta-circular JVM where the whole JVM was written in Java, right? And from that experiment, they found out that writing a GC in Java doesn't really make a lot of sense. All right, so it's my last slide, but it's important. So everything I've shown you so far is very cool and very nice, but most Twitter services are written in Scala, and that's one of the big issues, no, not issues, that's one of the big reasons why we are seeing this improvement, right? Remember the slide where I showed you how much the improvement is without escape analysis? Scala, compared to Java, allocates a lot of temporary objects when you write code, right? That's just the way it works. And if you do more inlining, and the inlining in Graal is just more powerful, we can remove more of these temporary objects. That's where most of the improvement is coming from, like 50%, you saw it. With Java, it's kind of a different story. I've seen both sides. I always say it's like a 50-50 chance if your Java application will run faster or not. I've seen benchmarks that run way faster with Graal than with C2. I've seen benchmarks that run about the same. And then I've seen benchmarks where it's actually worse. And the main reason for this is C2, and I've worked at Sun and Oracle many, many years on C2. Not one day, not 1 hour, or 1 minute did we spend on optimizing for any other language than Java. We always optimized for Java. So if you have another language like Scala, Kotlin, Groovy, Clojure, Graal might be better, right? And we can, as I mentioned earlier, my colleague Flavio, it's so much easier to write language-specific implementations in Graal than, let's say, in C2. So you should give this a try. I'll pitch this idea at the end of my second talk again, so please come all to that one. I'll massage you more to please try Graal, because it might help you as well, in whatever way, right? It might help you to save some money, improve performance. It's one of the reasons why I'm giving this talk and I'm doing all this talking about money is because you have to go to your manager and tell him, hey, there's this new shiny thing that I would like to try. And then he will say, but why? And then your answer would be, because it's shiny, right? But you can say, hey, look at this presentation from this Twitter guy. They're saving a lot of money doing this. So that's a good way to convince your manager. If they hear money, that, the dollar signs are rolling in their eyes. So that's one way to do it. And I think that was it. And the summary of my talk, and I have the same summary slide for all of my talks, it's this. If you run, as I said, on JDK 10 or later, this is all you have to do, right? So there is no incompatibility. So when I talk to some people after my talk, they're worried that if they turn this on, it doesn't work anymore because they think of native image. This is something completely different. This is like using another GC in Hotspot. If you suddenly use parallel GC instead of serial GC, right? Your applications still work, same thing. You will not notice that you run on Graal, except that it might be faster. That's all I had to say. And before I let you go, I'm not sure, I think I'll, hang on, let me try to do this. Can I do that? Yeah. Oh, no. Can you bring it back? Excellent, yes. So I'm going to pitch two things. Number one is, I live in Hawaii, if you haven't noticed. Hawaii hat. I have a small unconference that I run in Hawaii in January. I don't know how the weather is here in January. Not so warm, I think. So we were, this year in January, we were surfing at the beach, right? So I'm just saying, if you don't have anything to do in the third week of January, think about coming to Lava 1. I don't have the exact dates yet, but follow this account if you're interested. Come out to Hawaii. And then the other thing I wanted to tell you, oops, because I tweeted this the other day, and I think it's very helpful. I tweeted out the slides of my talk as a small video on Twitter. So if you go to my account, you'll find all the slides, and you can scroll through, scrub through them, and look at them. That's all I had. Thank you so much.
Thanks, Chris. Unfortunately, we are running out of time, so let's choose the best question. The only one question we have.
The best.
The best question, yeah.
It better be good, and about Lava 1.
One question.
Oh,
Don't be shy.
You scared everyone. No, it could be any question.
Oh, I see.
Someone has a question.
As you mentioned, the most important feature of Graal is its utilization of resources. Mm. And have you ever issued some degrade of this metric after fixing some bugs? And how do you actually measure and how do you test performance?
Let me think. I don't. So all the bugs I've shown you, I don't think they affected performance. But it's certainly possible that if you fix a bug, that performance will regress. That's possible. But it's always more. But that's okay because before it was not correct, right? It has to be correct before you optimize more, so that's fine. But I think that wasn't the case for us. All the graphs you've seen, I did not create these graphs. They are just screenshots from the metric system we're using internally. It's just it has a small query language. I type in a few queries, and then these things come up. So every time we fix a bug, bring in a new Graal version, or I don't know, we run an experiment like what I've shown you today, and then we look at all the important metrics. That's how we figure out if we have a performance regression or not.
And what about resource utilization?
You're mostly talking about memory?
About memory and CPU?
Yeah, same thing. Like, I didn't show you memory usage graphs, but we have that too, right? We look at memory usage. The way we do it, we have, what are they called? I can remember what they are called. Let me call them clusters, right? We have clusters of, let's say the tweet service, we have multiple of these clusters, so we can move either one instance or one cluster or one data center over to Graal or the new optimization, and then we compare it to another one. That's how we figure out if there is a performance improvement or regression, or we use more or less memory. That's what we do.
And do you do this on a regular basis or just after some feature rollout?
So we, the JVM team, the VM team, we only do this when we know we are changing something. Right? The service owners themselves, they do this constantly. Right? They look at their metrics every day. They have even some, watchdogs that complain when suddenly, I don't know, they use X% more of memory or something like this. So they know if something goes wrong.
Thank you.
All right, thank you.
Okay, thanks, Chris. Thanks for the brilliant question.